Today, I'm reviewing my game Glyph Gambit by walking through a real production codebase that was generated incrementally by large language models over about 4 months. The game works, it runs, it ships, and players can complete full runs. This is not a prototype or a tech demo, it is a functioning game. So this is not about whether AI can write software, and it is definitely not about so-called AI slop. Slop does not ship. Slop does not survive 4 months of iteration. Slop does not support full gameplay loops. What I am looking at instead are the kinds of issues that only show up over time in any real system. Type drift, unused pathways, integration assumptions that do not break immediately but quietly add fragility. On screen is a high-level view of the architecture. Gameboard orchestrates gameplay. Game state handles persistence and run-level memory. Piece manager and grid system manage board state. Data loader and save manager handle content and storage. This is a legitimate, conventional game architecture. It is not chaotic and it is not random. But once systems start interacting, consistency becomes critical, especially around data shapes. The first issue is in the combat system. In one part of the function, attack data is treated like a dictionary, using lookups and existence checks. A few lines later, the same object is treated like a resource with typed properties. Those are two incompatible representations. Why this matters is that either path can crash at runtime depending on what actually gets passed in. If a resource reaches dictionary logic, it can fail. If a dictionary reaches the resource path, property access fails instead. This is a classic large language model artifact. Both approaches are valid on their own, but the system never enforced a single representation across the boundary. The fix here is simple. Pick one data shape and normalize at the boundary. Either always pass a resource or always pass a dictionary, but never mix both in the same execution path. The next issue is also in the combat system. This function assumes that the board exposes a pieces collection. But the game board never defines that property. That tells us something important. This path is either no longer wired into live gameplay, or it was generated against an outdated mental model of the board. Why this matters is that dead paths do not fail tests. You can ship a working game and still have an entire system that breaks instantly the moment it gets reused. The fix is either to wire this system into the real source of truth, like the piece manager, or remove the unused system entirely. Leaving it half-connected is technical debt waiting to activate. Next is the save manager. When a save file is deleted, the in-memory save data is reset, but only to a partial schema. Several progression-related fields are missing. Why this matters is that if the deleted save was also the active one, and the game saves again before a full schema is rebuilt, data can silently disappear. This is not a crash. It is state corruption that only shows up later. The fix is to centralize a single authoritative default save schema and always reset to that structure. Moving on to the data loader. Cached JSON. Data is returned by reference. That means any caller can mutate the cached object and permanently affect all future callers. Why this matters is that bugs become order-dependent and extremely hard to reproduce. The system works until someone touches data in the wrong sequence. The fix is straightforward. Return deep copies of cached data or enforce immutability at the boundary. Finally, the test suite. Most tests validate arithmetic and isolated logic. That is useful, but it does not exercise full gameplay flow. Why this matters is that integration issues like the combat system wiring problem can survive a completely green test suite. One minimal integration test would help a lot here. Spawn a board, move a piece, apply an attack, and assert that state transitions are correct. To be clear, there are real strengths in this codebase. The content pipeline is data-driven and scalable. Systems are reasonably separated. Defensive checks reduce crash risk in dynamic scenes. This is not AI slop. What this code shows is that large language models can produce real, shippable software, but they do not enforce architectural intent unless a human does. The code works today. Without review, it can break tomorrow. That is the real takeaway.